Okay, so 8.4 is on electric or potential difference, also called voltage, and electric potential. So we saw with Coulomb's law that we represents a force between charges. And we can remember that a force exerted over a distance ends up giving us um, work done. So now, if you do something like stretch a string, tension will pull back. We'll want to pull it back to its original length. If you move massive objects away from each other, gravity will tend to pull them back together. And if you move charges away from each other, they might mean that they'll want to be pulled back together if they're opposite signs, or if they're both the same side, they'll want to move apart from each other. So in a sense, you have to look at both flavors of that, because you could have one where you have positive outward like so, and another positive here, and this he's gonna have this has a lot of potential energy. Wants to move away from the other positive, but a negative one, little potential energy. So you have to remember the signs of the charges when you're considering this. But if a particle is somewhere it doesn't want to be, then it has potential energy. And of course that can be converted to things like kinetic energy as it begins to move away. We saw in the last unit that the electric field equaled the force over charge. And so that can be rearranged for force equals the electric field times the charge. Potential energy for electric equals work, which would be that force over delta S. But if the force is E times Q, that can be written like so, where that is our electrical potential energy, which is saying here you have a charge in an electric field moves some distance. Okay? So let's look at an example for that. Okay, how much work is done in pushing 0.05 coulombs of charge 30 centimeters against an electric field of 150 newtons per coulomb? Well, the work done will equal our electrical potential energy, E times Q times delta S. Okay, so the electric field is 150 newtons per coulomb. The charge is 0.05 coulombs, and the distance is 0.30 meters. And when we multiply that out, we get 2.25 joules, Newton meters, joule. second thing we'll talk about here is voltage, okay, or the potential difference. So before we do that, well, no, let's do this. So we talk about energy per unit charge a lot, in the sense of being a useful construct with electricity. We could do the same with the gravitational field. We could talk about, energy per mass. We don't usually do that because our energy field, or our gravitational field, is constant around the surface of the Earth. But for electrical fields, they vary over short distances. So we call this the voltage, where we have the change in electrical potential over the amount of charge, Q, which could also be the work done over charge. And the work is joules, so this would be joules per coulomb, the units, and this is also called a volt. Of course, you've heard about 6-volt batteries or 12-volt batteries, 1.5 volts. So let's look at some physics symmetry first. We have mechanical versus electrical. In that sense, we had the equation for the gravitational field was our Fg over m, right? And it ends up on the surface of Earth to be about 9.8 newtons per kilogram, or meters per second squared. And then on the electrical side, we get the electrical field that was force per unit charge. And we saw that we had Fg was the constant g times m1 times m2 over r squared. And then for Coulomb's law, we had k times charge 1 times charge 2 over r squared. And then if we take for g here and divide this Fg here by m, we get big G times m over r squared. And the electrical field becomes, in the same way, k times q over r squared. Now for potential energy, we saw Ug was mg delta H. And U electric ended up as charge times electrical field times delta S. Now, if we wanted to define something similar to the voltage for gravitational field, we call it the liftage. And the liftage would be Ug over the mass. Where for the electric, it's the voltage, where it's UE over the charge. And rearranging that, we get liftage, or resubstituting, is G times delta H. We'll plug in mg delta H for that. And voltage, we can see by plugging in QE delta S, would just be E delta S for the voltage. So those are liftage and voltage. And this idea of voltage is like potential energy per, so it's like sort of on bleachers you can imagine going up, where you could have different size. So let's talk about liftage first, different size people, but they're all on the same bleacher, so they have the same liftage. Or in charge sets, electrical sense, they have the same voltage, even though that they have different charges. Um, so based on where they are in space. So it's a positional quantity. So we could also rearrange this to get a new formula for electrical field again, which is voltage over delta S. Let's look at an example. Okay, how much energy does a 2 microcoulomb charge gain in moving through a potential difference of 6 volts? Okay, so the energy from electrical would be equal to, if we bring these up, voltage times charge. So it's just a matter of putting volts in, which is a joule per coulomb, 6 joules per coulomb, over 2 times 10 to the minus 6 coulombs. And that gives us 1.2 times 10 to the minus 5 joules of energy. Now, when you take plates that are oppositely charged, okay, plus Q and minus Q, you can set up voltage bleachers between the plates. And the field between here, these charged plates, is quite uniform, or very uniform. It turns out the strength of the field is related to the voltage by the separation distance here, delta D, where the voltage would come like from a battery, and the separation would be, actually just D would be better instead of change in D. It's just a distance between the two plates, D. And so you can measure the electric field. So if you had something like a battery of 12 volts, and that was set up between two plates, we could measure the electric field between that. So let's say the separation was between these was 3 centimeters. And the electric field would just be V over D, or 12 volts over 0.03 meters. (400 voltmeters). A voltmeter must be the same as a joule per coulomb. Then we could say something like this too. If we had that amount of electrical field, we could ask the question, how much energy is gained by a proton traveling from plate A to plate B. Okay, so that potential energy is going to become kinetic energy. So the U, E, E, Q delta S. Well, we know what E is. We looked it up, or we solved for it before, 400 voltmeters. The charge on a proton in your reference table, 1.6 times 10 to the minus 19 coulombs. And that separation difference of 0.03 meters would give us the amount of potential energy available is 1.92 times 10 to the minus 18 joules. Oops. And so if our energy initially equals our energy finally, that's going to become our kinetic energy, 1.92 times 10 to the minus 18 joules when it gets there. So we could ask the question, how fast? Well, in that sense, K, you remember, is 1/2 mv squared. So 1.92 times 10 to the minus 18 joules, 1/2. The mass of a proton, I'll have to look that up. The mass of a proton, which is 1.6 times 10 to the minus 27 kilograms times v squared, 27. So v squared will be 2 times 1.92 e to the minus 18 divided by 1.6 e to the minus 27, 3, 6, 9, 2.4 times 10 to the 9 meters squared per second squared, square root it, gives 48,990 meters per second from that kinetic energy that's available. Okay.